So this is a meeting for young statisticians, and I will actually not be giving a talk in statistics myself. Instead, I am working in theoretical probability theory. But as far as I've understood, there are also many people here with interests in probability theory, and I will try to make the talk as accessible as I can, also for those who work primarily in statistics. So my talk will be about random curves and surfaces, and it will have two parts. In the first part of the talk, I will introduce various uniformly sampled random objects. So I'm considering some class of objects, for example, the space of curves, the space of functions, some space of surfaces, and then I want to, in some sense, sample some object uniformly at random from this set. And then in the second part of the talk, we will be studying an important or a very powerful tool to study the surfaces in the first part of the talk. And this tool is known as conformal welding. So we start with the first part, and we start by asking a motivating question. So how can one sample a curve uniformly at random? To answer this question, we first need to say what we mean by a curve. One precise mathematical definition of a curve is to say that the curve is the image of an interval to a topological space by a continuous function. So to make this a bit more concrete, we can fix the interval and we can fix the topological space. For example, we can say that the interval is a unit interval, and we can say that the topological space we consider is just the set R of real numbers. So with this choice, then this set omega is our set of curves. So here is our omega, and then we want to sample an element from this space omega uniform at random. So it's not obvious how to do this because omega is an infinite set. It's even an infinite dimensional set. So it's not obvious how to sample an element uniformly at random. So our approach to this problem is to discretize it. So we consider curves which are piecewise linear. We fix some natural number n. We divide the unit interval into shorter intervals of length 1 over n. And then we require that the function is linear on each such smaller interval and with slope plus minus root n. So this space will be, so the set of functions will be finite if we also require that functions equal to 0 when the input argument is equal to 0. So from the set omega n, we can easily pick a function uniformly at random, and we send n to infinity. So a classical result is that if we do this and we send n to infinity, then in the limit, our random curve is given by the random fractal curve known as a Brownian motion. So here are 3 independent samples of Brownian motion. So Brownian motion, as many of you know, it's a random curve which is arising in a huge number of different settings and applications. So it's used to model everything from financial markets to a number of physical phenomena. So one reason that Brownian motion is appearing in so many different settings is universality. So universality means that it describes the asymptotic behavior of a very large class of discrete models, typically such that the asymptotic behavior of the discrete model is not too sensitive to the exact definition of the discrete model. So then we ask, how can we sample a self-avoiding curve in the unit disk uniformly at random? So now we're interested in curves in the unit disk. So we want that our function is taking values in a closed unit disk. And then we want our curve to be self-avoiding. So this simply means that the curve is, that this function is injected. As one example of such a curve, you can see in this figure. So now we want to sample some element uniformly at random from our set omega, and again, it's not obvious how to do this because omega is infinite. And just as before, our approach to the problem is to discretize it. So we consider some rescaled version of Z2, and we restrict it to the unit disk. And then we consider functions on this lattice. And we require that the function is that our curve is starting at -I and ending at I. And we're also requiring the function to have speed n to the power third. So the reason we would choose this particular speed is that we need to do this rescaling in order to get the limit that we want. So it is for a similar reason as we needed the slope to be plus minus root n in the setting of the Brownian motion. So the choice of speed is essential. This choice of starting and ending points plus minus I is actually not so important, but it's simply a choice I make in order for for what I will say next to fit better with the standard theory. So we have defined our set omega n of such discrete curves, and we sample a curve uniformly at random from this set omega n. So here I've done it for one choice of n, and here I've done it for some larger choice of n. And then it is believed, but actually not proven, that when n is sent to infinity, then the random curve sampled in this way, it converges to the random fractal curve that we call the Schramm-Loewner evolution. So what is the Schramm-Loewner evolution? So the Schramm-Loewner evolution, it is a family of random fractal curves introduced by Otto Schramm almost 25 years ago. The Schramm-Loewner evolution, it describes the asymptotic behavior of a number of curves in statistical physics models at criticality. For example, it describes the asymptotic behavior of curves in the Ising model, or interfaces in the Ising model, interfaces in percolation, interfaces in the uniform spanning tree, and so on. The SLE curve is uniquely characterized by two natural properties known as conformal invariance and the domain Markov property. So Otto Schramm, he was studying a number of different statistical physics models, and he realized that the various models he studied, they were believed to have scaling limits with two properties in common. And this was exactly this conformal invariance and this domain Markov property. And he argued that there is a unique one-parameter family of curves satisfying these two properties, and therefore these curves are exactly the candidates for the scaling limit of the discrete models. After Schramm's introduction of SLE, it was proven that these SLEs they do describe the asymptotic behavior of many discrete models. So the convergence result on this slide is only conjectural, but for these other models mentioned on this slide, the convergence has been proven rigorously. So the SLE, as mentioned, there is one parameter family of curves satisfying these two properties, and the parameter is denoted by kappa. In the figure, I have sketched SLE for kappa equals 2 and kappa equals 4, and the parameter kappa is governing how windy or fractal the curve is. As when we increase the value of kappa, the curve is getting more and more windy and fractal. While in the limit, as kappa goes to 0, the SLE is deterministic. So there are many different variants of SLE. Here we consider what we call a chordal SLE. So this is a variant of SLE defined in some simply connected domain, connecting two marked boundary points. Whereas we can also consider other variants of SLE, such as, for example, the SLE loop that I have drawn here. So this is a variant of SLE which has the same local properties as the chordal SLE, which is shown here. But as you can see, it has a different global shape since it forms a loop. One can define the SLE loop on many different domains, and here I have drawn it on the sphere S2. It is believed that the SLE loop is uniquely characterized by some natural set of axioms in a similar spirit as the chordal SLE, but the uniqueness question is actually still open. So then we ask, how can you sample a function on the unit square uniformly at random? So again, our approach to the problem is to discretize it. So we consider some rescaled version of Z2 restricted to the unit square. And then we consider functions defined on this graph. So in order to get some finite set of functions, then we require that the function takes only integer values. We also require that the boundary data are 0. And then we're hoping to take some kind of limit when the lattice size is going to 0. And therefore, it's also natural to require that adjacent function values are not too different. And we are requiring that adjacent function values are differing by at most 1. So there are finitely many functions which are satisfying these properties, and for a given lattice size, and we're imagining that we're picking such a function uniformly at random. So here in this figure, we have chosen a function uniformly at random, satisfying the constraint I was just mentioning. So then we can ask what happens in the limit as the inverse lattice size of 1/n is sent to 0. So first, in the figure, you can see simulations for two different values of n. At least these figures are showing roughly what one sees for two different large values of n. So the function is only defined on these vertices of the graph, but one can extend it via some continuous interpolation to the full square. So when we increase the value of n, then the typical then the fluctuations are getting so the frequency is getting higher and higher, and also the height of the mountains and the depth of the valleys is getting larger and larger. So what can be proven is that if we fix some point z in the bulk, then the absolute value of the function at this point, it will be some random variable. And this random variable, it will have an order of magnitude of order square root log n. So at least this was proven if we consider this model on the triangular lattice. And then it is conjectured but not proven then that if n is going to infinity, then the function h sub n, it converges to a continuum random function known as the Gaussian free field. To be more precise, this Gaussian free field is actually not a random function. Instead, it is a random distribution or a random generalized function. So this means that with probability 1, if we have some fixed point z, then h of z is not well defined. So we can see why this should be the case if we look at the discrete model, because if we fix some point z, then the discrete function is actually diverging. So it's going to plus minus infinity at any fixed point z. So we see that any limit of this discrete model, it can't be well defined pointwise. But what one can argue is that if f is some smooth test function, then the integral of f against h is well defined. So this integral of h against f, this will be some random real number, and the law of this random variable will depend on the choice of smooth test function f. To be more precise, one can argue that h is an element of the sublet space h minus epsilon of s for any epsilon greater than 0. So if we set epsilon equal to 0, then this is simply an L2 space of functions. So we see that this Gaussian free field, it almost has the regularity of a function, but not quite. As mentioned, the integral of h against f will be some random real number. To be precise, it will be a normally distributed random variable, and it will have a mean 0, and it will have variances and covariances depending on the choice of test function f. So precisely the covariance between these two integrals for test functions f and g, it will be given by this formula, where g is the Green's function associated with the Laplace operator on s. So we have seen that both the SLE and the Brownian motion, they describe the asymptotic behavior of a number of discrete models. So they are universal random objects, and the Gaussian free field is satisfying a similar universality. It has been proven that it describes the scaling limit of fluctuations in a number of statistical physics models. For example, fluctuations in the characteristic polynomial of certain random matrices, and also fluctuations in domino tiling height functions. Another reason that the Gaussian free field is interesting is because one can argue that it is a natural generalization of Brownian motion to the case of higher dimensional time. So you may remember that the Brownian motion, so it is a function from a random function from some one-dimensional set to some one-dimensional set. If we look at this discrete model converging to a Brownian motion, then if we pick a two-dimensional time set, then we get exactly the model that we're considering here. And for this reason, one can view this Gaussian free field as a generalization of random motion to, in this case, two-dimensional time. One can also do similarly in even higher dimensions. Finally, a last reason that the Gaussian free field is an interesting object is because it appears in various constructions in conformal field theory. Okay, so then we ask, how can you sample a surface uniformly at random? I want to argue that a natural answer to this question is to consider a uniformly sampled planar map. To be more precise, a planar map is a graph which has been drawn on the sphere, which is viewed modulo continuous deformations. So for example, in this figure, you can see 3 planar maps. And this planar map and this planar map are considered to be the same planar map, since one can get one planar map from the other by doing a continuous deformation. On the other hand, this planar map and this planar map, they're not considered to be the same. So viewed as graphs, these 2 planar maps are the same, but viewed as maps, they're different, because in order to get this planar map from this planar map, then this edge has to be moved here, and this deformation is not considered to be a continuous one. So if we have some natural number n, then we can consider the collection of planar maps which have exactly n edges, and we can pick a planar map from this collection uniformly at random. So if we do this, then you get approximately what you see here. As mentioned on this slide, the planar map is only defined modulo continuous deformations. So therefore, if you have a planar map, it's not obvious how to draw it. In this planar map, in this figure, the planar map has been embedded into R3. So if we have a planar map, a large planar map, then it's typically not possible to embed it isometrically into R3. So it's typically not possible to draw it in R3 in such a way that all the edges have exactly the same length. So when drawing this planar map, then one has done some optimization of the drawing such that all the edges have a length which is as close as possible to each other. So one has done an embedding into R3, which is in some sense as close to isometric as possible. Okay, so the planar maps, they have been studied in many different branches, both of math and physics. In the math literature, the study of planar maps goes back to the combinatorics literature in the 60s. So here, Tutmoulin and others were proving enumeration or counting formulas for various planar maps. Later, they have been studied in, for example, geometry and in random matrix theory. An application very relevant for this talk is in random geometry, where probabilists are interested in understanding the geometry of large random planar maps. Another relevant application is in conformal field theory and string theory, where planar maps are viewed as models for random surfaces. So here we have some large random planar map with n edges. And a natural question is whether this planar map is converging in some sense when the size n is n to infinity. So when talking about convergence results for planar maps, there are many different notions of convergence that one can consider. And the notion of convergence that I will be focusing on is convergence under conformal embedding. There have also been proven a number of other convergence results in other topologies, but I will just focus on the conformal topology. So to explain what we mean when we talk about convergence of planar maps, then I first recall the uniformization theorem. So this is a generalization of the Riemann mapping theorem to the setting of Riemann surfaces. Suppose that we consider some simply connected Riemann surface M. Then there exists some conformal map from M to either the unit disk, the complex plane, or the sphere S2. So next we can observe that if we have some planar map, then it can be viewed as a Riemannian manifold, and in particular a Riemann surface. So I will be considering the special case of what we call a triangulation, So a triangulation is a planar map where all the faces have the shape of a triangle. So we can observe that this triangulation defines a Riemannian manifold, and in order to observe this, we can consider a collection of standard equilateral triangles, and then we glue these together according to the combinatorial structure of the planar map, and this will give us some Riemannian manifold. So each of these triangles, we equip it with a metric of the standard equilateral triangle. And then when we glue them together, then we will get a Riemannian manifold, which will be smooth everywhere, except that we will have some conical singularities at the vertices of the triangles if the number of triangles that come together is different from 6. So we have this Riemannian manifold, and we can apply the uniformization theorem to argue that this can be conformally, or this can be sent by a conformal map to either the unit disk, the complex plane, or the sphere. And since our planar map has the topology of the sphere, then the conformal map will also be to the sphere. So here I've illustrated such a conformal embedding. So here is the planar map that we saw before, and here this planar map has been embedded into the sphere S2 via such a conformal map. So the convergence result that I was just formulating. So this is conjecture to hold in a very broad variety of settings, and it has been proven in just for a very limited number of settings. So in the setting of uniformly sampled planar maps, it has been proven when we are considering triangulations, and it has been proven when we do the embedding via what we call the Cardy Smirnov embedding. So it means that when we do the embedding of the planar map, we're actually not applying this uniformization theorem. Instead, we're finding some other way to define some discrete conformal embedding, and then which we call the Cardy Smirnov embedding, and then we're using this method to draw the planar map on the sphere S2. So here in this figure, you can see our uniform ensemble triangulation, which has been embedded into the sphere S2. And you should imagine that it has been done by this Cardy Smirnov embedding, although the figure is not exact. So when we embed the planar map on the sphere, then we get an area measure on the sphere, and we also get a distance function or metric on the sphere. The Riemannian manifold that we have here, it comes equipped with an area measure and also a metric or distance function, which can be used to measure the distance between pair of points. And the area measure is simply obtained by just considering. So this is the standard equilateral triangle, and we just consider the Lebesgue area measure on this equilateral triangle. When we find the area measure on the sphere, then it's natural to rescale the area measure such that each face has area 1/n. So this is natural because the total number of faces will be of order n when n is n to infinity. So if each face gets area 1/n, then the total area of the sphere will be of order 1 when n is n to infinity. So we can also consider a distance function or metric on the sphere. So this is just given by. So this can be given just by the metric on each triangle. And then when rescaling distances, then we choose to rescale them by n to the power minus a quarter. So it's far from obvious why we want to use this this particular power 1/4. So if we had been in the standard Euclidean geometry, then if we are rescaling areas by n, then we actually want to rescale distances by root n. So you see that we actually get a different power. We have 1/4 instead of 1/2. But it turns out that this power 1/4 is the one we want to use, and this is illustrating that we have a very different that this random planar map is defining a very different geometry from the standard Euclidean geometry. So what has been proven in this special case of triangulations and this Cardy-Smirnov embedding is that when we send n to infinity, then this area measure mu sub n and this distance function or metric d sub n converges to some limiting area measure mu and some limiting metric d, which are both random. And this is the area measure and the metric associated with what we call a Liouville quantum gravity surface. So what is a Liouville quantum gravity surface? Heuristically speaking, we can view it as the 2D Riemannian manifold, where the metric is given by e to the power gamma h times the standard Euclidean metric. So here, gamma is some number between 0 and 2, and h is some variant of the Gaussian free field. LQG surfaces, they were first introduced by Polyakov in the context of string theory, and in recent years it has been a very active topic of study in probability theory. So how are these surfaces defined more precisely? To be a bit more precise, then we still let gamma be between 0 and 2, and now we let h be some Gaussian free field in some concrete domain, for example, the unit square. And then, as stated on the previous slide, so heuristically speaking, the LQG surface is a surface which has this metric. So what does this mean? So it means that it is the LQG surface where the area measure is given by the standard Lebesgue area measure reweighted by e to the power gamma h. It is the surface which has a length measure along its boundary, just given by the standard Euclidean length measure, locally rescaled by e to the power gamma h over 2. And it also comes along with a metric or distance function, which is just given by the standard Euclidean distances, but which are locally rescaled by e to the power gamma h divided by d sub gamma. So here d sub gamma is the dimension of the surface. This is the numerical formula for this is actually not known, or the exact formula is not known, but is known to be some strictly increasing function of gamma, which is strictly greater than 2 for all values of gamma. The definition of this LQG surface, it doesn't make literal sense because h is a distribution and not a function, so it's not obvious what e to the power some constant times h means. But one can argue that these two measures mu and nu and this metric or distance function d can be defined rigorously via regularization of the field. So the idea is that we let h sub epsilon be some distribution which can be viewed as an approximation to h, which is such that the approximation, so that h sub epsilon is converging in some sense to h when epsilon is set to 0. Then we can use h sub epsilon to define, for example, an area measure, because h sub epsilon is a smooth function, and then one can argue that this area measure is converging upon some appropriate renormalization when epsilon is sent to 0. So the construction which is shown here, so this is our rigorous definition of the area measure mu, and the boundary measure nu and the metric or distance function d can be defined via a similar regularization. So the construction of measures mu and nu of this type, so this is classical and goes back to the 70s and the 80s. The construction of the metric d, on the other hand, is a much harder problem, and it was actually only completed a few years ago in the works mentioned here. So the construction of the metric is much harder, because in order to find the distance between two pairs of points, then we want to find the shortest path between this pair of points. So when defining the distance, we need to optimize over all possible paths which are connecting this pair of points. Okay, so this is an illustration of the LQG area measure. So this is the random area measure whose density relative to the Lebesgue area measure is heuristically given by e to the power gamma h, where h is a variant of the Gaussian free field. So the different colors here are representing, heuristically speaking, you should think of it as the density of the random measure relative to Lebesgue area measure. So in these red regions, so these are the high density regions where this Gaussian free field is very large. whereas these dark blue regions are the low density regions where the Gaussian free field is particularly small. So I'm saying that these colors, heuristically speaking, represent density. So this is actually not a mathematically precise statement, because one can argue that this area measure is actually singular with respect to the Lebesgue area measure. So this tuple, mu comma nu comma d, it describes the geometry of the gamma LQG surface. So remember that mu and nu are measures, and d is a metric. So when we work with these LQG surfaces, then we typically want to view them as abstract surfaces that can be embedded into the complex plane in various different ways. So in this figure, you can see one LQG surface which has been embedded into the complex plane in two different ways. So here it has been embedded into the unit disk, and here it has been embedded into some other domain U. And we view these two surfaces as the same, because if you look at the measures and the metric in the right part of the figure, then this is just the push forward of the measures and the metric in the left part of the figure under some conformal map phi. So one can get many different variants of LQG surfaces by considering different planar map models. So earlier we were considering planar maps with the topology of the sphere. So in the limit, this gives what we call an LQG sphere. So this is a particular variant of an LQG surface, which has been defined by considering the Gaussian free field on a sphere. One can also consider planar maps with a topology of a disk. So you see that this is a planar map which has a macroscopic boundary, which is this curve shown in red. And when the size of this planar map goes to infinity, then it converges to the LQG surface known as the LQG disk, which is defined by considering some variant of the GFF in a disk. So far we have been studying a range of random objects. So we have been studying the Gaussian free field, which is some random generalized function. We have seen this Liouville quantum gravity surface, which is in some sense a random 2D Riemannian manifold, and we have also been studying the Schramm-Dömer revolution, which is this random non-crossing curve. So one thing all of these objects have in common is that they, in some sense, can be viewed as planar or two-dimensional objects, and in some sense they are living in a plane. Another thing that all three objects have in common is that they have interesting conformal symmetries. And finally, a third property they have in common is that they are describing the scaling limit of a large class of discrete models. So we see that since these objects have a number of properties in common, and since they have so many properties in common, it's maybe not surprising that there are a number of interesting interplays and relationships between these objects. And in the rest of the talk, we will be looking at some of these interplays. So I will now be starting the second part of the talk, where we will be considering conformal welding of these LQG surfaces that I was defining in the first part of the talk. So first, I want to explain what conformal welding is. So to do that, I consider two copies, D1 and D2 of the unit disk, and then I assume that I have a homomorphism from the boundary of D1 to the boundary of D2. And then a conformal welding, it is a conformal structure on the sphere, which is obtained by identifying the boundary of D1 and the boundary of D2 according to phi. So in some sense, we're gluing together the two boundaries, and in this way, we're forming a topological sphere. So when we're forming this sphere, then it's clear that if we look at the sphere away from the curve eta describing the interface of the two original spheres, then the sphere will have a unique conformal structure. So this is the conformal structure which has been inherited from the disks D1 and D2. But what is not clear is that we also have such a unique conformal structure across this curve eta, and we can also when we can talk about both existence and uniqueness of this conformal structure. So this conformal welding problem, it is a classical and hard problem in analysis, and in general, both existence and uniqueness may fail. But if one has sufficient regularity of either phi or of this curve eta, then this guarantees the existence of a unique solution. So So we are interested in conformal welding results in the setting of LQG surfaces. So I will start by explaining one example, which was proven in a recent work with Ang and Sun. But I should emphasize that our proof is building on a number of other works, also by other people. So we start by considering two LQG disks. So these are LQG surfaces with disk topology, and we want to weld these two LQG disks together. And we're doing and we want to do this conformal welding according to LQG boundary length. So remember that if we have some LQG surface with a boundary, then it has some boundary measure, which allows to measure distances along the boundary. And we want to do the welding according to this boundary measure nu, such that if we have some small boundary segment of length epsilon here, then it should be identified with some small boundary segment of length epsilon on the other disk. So in our work, we're arguing that this conformal welding operation, it's well defined, and we also give an explicit description of the object that we get when doing this welding. So what turns out is that when we weld these two disks together, then we get exactly the LQG surface known as an LQG sphere, and the interface between the two original disks is given by an independent SLE loop. So you see that this result is containing a number of different claims. So first of all, it's far from obvious that the sphere one gets has exactly this law. It's not obvious that the interface has exactly the law of the SLE loop. But the thing which is maybe the most surprising at first sight is this fact that this LQG sphere and the SLE loop are entirely independent of each other. So a priori, there wouldn't be any reason why they would be independent when you look at the two original disks. Okay, so so the proof of this result is building on the results stated on this slide. So here we also want to glue together two disks. But now we only want to glue together this purple boundary arc to this purple boundary arc. So now we're arguing again that this operation is well defined, and we argue that the resulting object is a third LQG disk decorated by an independent chordal SLE curve. On this slide, I am showing an exact discrete counterpart of the result on the previous slide in the setting of planar maps. So the figure is illustrating that you have a bijection between the objects on the left and right sides of the equality. So on the left side of the equality, we have a pair of planar maps, each with the topology of a disk, and each planar map has two marked points on its boundary, and we require that the length of this blue curve connecting the two marked points is equal to the length of this blue curve connecting the two marked points on the other map. But otherwise, the maps can be arbitrary. On the right side of the equality, then we have a planar map with the topology of a disk with two marked points on the boundary, and it is decorated by a self-wording path connecting the two marked points. And the projection, of course, works by just taking these two planar maps and then identifying the two blue curves. So this projection, it is an exact discrete counterpart of the result on this slide. In the special case when gamma is equal to the square root of 8/3. So if one looks at the objects here and one sends the size of the planar map to infinity, then it converges in the scaling limit to exactly the objects that you see here. And one gets LQG for the special case when this parameter gamma, so this is the parameter appearing in the exponent with this special parameter is equal to the square root of 8/3. So when proving conformal welding results, then one is typically very inspired by discrete results of the type explained here. And if one knows this projection and also a few other closely related projections, then it's also hard to guess that the result on this slide is true. But I still want to emphasize that the welding results, they are typically proven purely in the continuum, only by continuum techniques without any concrete inputs from planar maps. So the two results I cited so far, so they are just two among a large number of welding results that have been proven in recent years. So conformal welding results in the flavor that I was presenting here. So it goes back to this work of Sheffield from 2010. So he was gluing together two surfaces with half-plane topology in order to form a third surface with half-plane topology. Here is another result, which was proven in a work by Duplantier, Miller, and Sheffield. So they consider a surface with half-planar topology. They're gluing together the left and right boundary arcs, and they're getting a particular surface with whole plane topology, which is decorated by an independent SLE curve from connecting 0 and infinity. And these figures illustrate some other results that I will not go through in detail. So the various conformal welding results, they have certain general properties in common. So the general setting is that we consider some LQG surface, and we cut it into two or more smaller LQG surfaces via independent SLE type curves. And then if we have chosen these SLE type curves appropriately, then the smaller surfaces, they will be independent of each other. And it's also typically the case that if we know the smaller LQG surfaces, then we can recover the original LQG surface via some variant of conformal welding. And it's typically also the case that there are discrete counterparts in the setting of planar maps. Due to time, I think I will actually not describe the next example in detail, but I can just I can just mention that one can also do a welding of trees in a similar way as surfaces. So here we have a particular random tree known as a continuum random tree, and then in a work of Duplantier, Miller, and Sheffield, they were studying the mating or welding of two continuum random trees. And they were arguing that the mating or welding of two continuum random trees is well defined, and that maybe surprisingly at first sight, it actually gives something with a topology of a sphere. And the object will be a gamma LQG sphere, which is decorated by a space-filling variant of SLE. So a variant of SLE, which is hitting every single point of the sphere. And just as before, this space-filling SLE can be viewed as the interface of the two trees. So conformal welding, it has been extremely powerful to study both LQG, SLE, and planar maps. This slide is giving some overview of some of the applications. So for example, conformal welding has been very important to prove convergence results of planar maps to LQG. So actually all convergence results of planar maps to LQG that we currently know are building on ideas from conformal welding. Another application is the study of statistical physics models on planar maps. For example, one can study scaling limits of statistical physics models on planar maps. One can establish various exponents of statistical physics models on planar maps, and so on. It has also been very important to prove that the LQG surface has a distance function or a metric in the special case when gamma is equal to the square root of 8/3. Later, it was proven via a completely different method that one actually has such a distance function for all values of gamma. It has also been used to prove integrability results for SLE and LQG and Lie will CFT. So the idea is that in the study of SLE, in the study of LQG, and in the study of Lie will CFT, one has various methods to obtain exact formulas. So when I talk about integrability, I mean exact formulas. So you have all these methods for obtaining exact formulas, and then by using the interplay between the LQG and the SLE, which appears in the conformal welding, then one can, for example, get an exact formula for SLE by using some exact formula for LQG and vice versa. One can also obtain a number of other results on SLE, and one can also and it also turned out to have a number of other applications. So I'm not sure I will have the time to say this, but yeah, for example, it has been so one thing I was planning to present is an application to the study of random permutations. Okay, so why is conformal welding so powerful? So at a high level, one can say it's powerful because one can exploit this interplay between LQG and SLE, and also because it allows to study complicated surfaces by decomposing them into smaller pieces. Okay, so I was thinking to also present two examples. I think I will actually not really have the time to do that, so I will just mention like very briefly what like on a high level what this is. So the first application was to the study of the self-avoiding loop on planar maps. And one can argue that in the setting of, so remember that proving that like these self-avoiding walks converge to SLE at thirds, it's a very difficult problem on lattices. But it turns out that in the setting of planar maps, one is able to prove such a convergence result. So one can consider a planar map with a uniformly, or with a loop, the self-avoiding loop, so that if one condition on the length of the loop, then all possible realizations of the loop have the same probability. And one can argue that this loop is actually converging to the SLE out-thirds loop in a certain sense. Yeah, so this is a loop version of the result, but earlier corridor results were proven in these works. So the second application I wanted to present is an application to the study of random permutations. So it turns out that we can prove a new formula for a particular family of random permutations known as Baxter permutations. Yeah, so I will not present due to time. I will not present this in detail, but I can just mention on a very high level. So why can we use LQGs to study random permutations? So the reason is that random permutations, so they can one can study the scaling limit of random permutations, and it turns out that they can be described by a particular SDE. And it turns out that this SDE, it turns out to also arise in this setting of conformal welding. And then the observables, one is interested in on the permutation side, it turns out that they correspond to computable geometric observables on the LQG side.
Nina, I'll just briefly interrupt. SDE is stochastic differential equation, right?
Yeah, that's right.
Okay,
yeah,
okay. Thanks.
Differential.
Just to be clear.
Yeah. Okay, so I think yeah, my time is actually out now, so I think I will just be open for questions. Yeah, I'm sorry that the last part was very quick.
No worries. Thank you. It was more than on time. Thank you. Thanks a lot for your clap, and a great one. Thank you. So we will open naturally the space for questions. I will start with 2 or 3 mine, and then hopefully to stimulate the debate. Firstly, you mentioned during the talk that there exist other topologies apart from the conformal one, if I understood you correctly. What kind of them are they, and could study of the properties of SLE type objects that you have shown change, or what would a study in these different topologies mean for such studies? Secondly, you mentioned the power of conformal welding, also mating of trees. Are there any other possibilities related to derived similar results that have been derived using such approaches? And thirdly, so in terms of the applications, so just to recollect, so what kind of applications basically are possible using such approaches? There are applications naturally in mathematical physics, which we didn't touch in detail, say using string theory, and what kind of applications are possible here? They're all in 2D, so what is possible to study with the approaches that you mentioned? Thank you.
Okay. Yeah, so yeah, so I can start with the other topologies. So yes, I mentioned there are a number of different topologies that one can one can use. Okay, let me see. It's actually here. Yeah. Okay, so there are many different notions of convergence, and here I have this convergence and conformal embedding. So I would say that there are two other notions of convergence that are quite commonly considered for planar maps. So one such notion of convergence is convergence of the planar map viewed as a metric space. So metric space, it's just some set where when one has a function which allows to measure the distance between any pair of points. So one can view the planar map as a metric space just by equipping it with a graph distance. And then one can ask if this is converging in some sense when the size of the planar map goes to infinity. And in the setting of these uniformly sampled planar maps, then it has been proven that actually a large class of different planar maps converge in this metric topology. So to be more precise, it's called the Gromov-Hausdorff topology. And this is going back to work of Le Gall and Mirmont. So they were the first to prove such result for certain classes of planar maps, and then it has later been extended to a number of other planar maps. So this gives convergence to what we call a Brownian surface. So a Brownian surface is just it's a family of random metric spaces. So this has so far only been proven in the setting of uniformly sampled planar maps. Since there are also a number of other probability measures one can put on planar maps which are non-uniform and which should also give gamma LQG in the scaling limit, but in those settings it's still open. And then so in other so this is one topology. There is also another topology that one has been considered, which is what is called mating of trees topology. So the idea in the mating of trees topology is that certain planar maps. So it's a general belief that if one has a planar map with some critical statistical physics model, then it should converge to LQG, such that the value of gamma for the LQG depends on the universality class of the statistical physics model. And if one in this example, if one looks at just the marginal law of the planar map under such a probability measure, then this is will be such that the probability that our random planar map is equal to some fixed planar map will be proportional to the partition function of the statistical physics model on this fixed planar map. So in many settings, one can argue that there is some bijection between the planar map with statistical physics model and some random walk, and then this random or a pair of random walks. And then this pair of random walks, they typically converge in the scaling limit to a pair of random motions. And then one thing I didn't quite explain, but which is the case, is that this continuum random tree that I was studying here, it is defined via Brownian motion. So it means that on a discrete level, so the planar map with statistical physics model, it can be viewed as like a discrete welding or mating of two trees. And one has the same in the continuum. So the idea is then that the planar map with statistical physics model converges to the SLE, to the LQG with SLE because the associated trees are converging. So these are two other notions of convergence, and these notions of convergence, they are encoding completely different set of information. So there is just it's just a very different set of properties that is encoded. Did you have some other question about this? Like
no worries. So also about these mathematical physics applications, and possibly if there is other approach apart from mating of trees and welding, but shortly to give other also the question possibilities.
Okay. So I can just first comment briefly on the physics. I think that one of the big achievements of this theory is to just provide like a solid mathematical foundation for the theory. So of course, if one looks in the physics literature, it's not obvious. So the theories are not mathematically. It's not mathematically rigorous. It's not defined in a mathematically rigorous way. So I think one of the key achievements is to just give give a solid mathematical foundation for the theories. And then of course these techniques, they also provide rigorous proofs of particular properties conjectured in the physics literature, and there are also examples where certain things were introduced in the math literature which haven't really been fully developed in the physics, even on a non-rigorous level. So this is just a very high level, like broad answer. So going to your, I think it was the second question. So I'm not sure I fully understood it. So you said something about other applications of mating of trees.
Maybe, Nina, if we can actually continue discussions and so on, but maybe also if any other participant has a question, and then hopefully to continue debates. Thank you for a great lecture. Just to repeat. Anybody, please just raise your hand or put a question in the chat. Those are slightly different topics, possibly from some talks in probability that we had, but they relate to Brownian motions, to excursions that you mentioned, and to other things that participants presented. So please free any question, as we mentioned, is more than welcome. We still have. I will ask one additional one, but if anyone has anything, please do. Your talk, I think, was based on the chordal SLE, right? The full construction. Is it possible to construct everything, I would say, or parts also on the radial version of the SLE, which we didn't discuss a lot?
So if the question is like radial welding results for radial SLE, so this is actually this was actually done very, very recently. So like two younger researchers named Maurice Ang and Puyu, so they have actually very recently achieved this. So they have done a welding which involves this radial SLE. And it's not a trivial construction. It's technically quite challenging. It's building on these chordal results, but it requires also a number of other novel ideas. And it was actually conjectured earlier in work of Wiklund and Wang that there should be such a radial welding, and then it was then recently established by Ang and Yo.
Okay. Thank you. Thanks. Any further question?
So I'll try to make one question, but I don't know if it's a stupid one. So I can see this relation with with the sphere, and I know that there are some works on random geometry on the sphere, in the sense there are works that study, for instance, boundary length, the area of random fields on the sphere. Is there maybe any connection in the sense that maybe this embedding can be used to generalize that results on planar surfaces, planar random surfaces? I don't know if I'm really not on the topic, so it was just something that came into my mind. Thanks.
So I guess it depends. As you mentioned that there are like other works on like random fields on the sphere. So what kind of fields do you have in mind? Do you have some examples of other fields on the sphere?
Like Gaussian random fields on the sphere, for instance.
Yeah. So do you know how they're typically like smooth fields or like?
Yeah, maybe like with continuous covariance or like isotropic
Yeah,
random.
yeah, yeah. So I would say that it's relatively different because the like here we're considering like fields given by a Gaussian free field, which is like a very rough field, whereas these like smooth Gaussian fields, I mean typically they're behaving just very differently as compared to the Gaussian free field. So I would guess in general it would be hard to transfer many results between those settings. Yeah, so I guess my answer is that I don't really see any way. I mean, in most cases, I think it's hard to get new results. Uh, yeah. Obviously, there could be certain proof techniques that would happen to overlap. But yeah. But I think in most cases, it would not be easy.
Okay, thank you.